Hey everyone, it's MG from Computer Science 315. Let's talk about storage concepts. Storage concepts are incredibly important because if we don't fully understand sort of the baseline ideas and concepts, then we are doomed to be reformatting and re-imaging and just generally misunderstanding how things are with our systems. So, previously in a hardware lecture, we talked about how everything eventually it returns to hardware. Everything eventually becomes or is hardware. And while that can be awesome, it can also be a pain. The least of which is you're racking and stacking in a data center and you're cutting your hands up because everything in a data center is designed to, you know, cut and kill you. You would think server hardware is sharp and will cut you. That is not a joke. It is, it's not all the nice brushed aluminum Apple products that you would expect. They're getting better, but consider that this is not supposed to be touched very often. If you can DIY it, you could DIY buy it. Whoa, it's a sad joke. Cabling is really important, mainly because heat and airflow is very important. And data centers can get messy, as seen in those ladder slides on the previous presentation. Go back if you don't know what I'm talking about. We're going to be seeing a slide very similar to this, several permutations of variations of this slide. And this is to explain that OSs and hard drives and storage and operating systems and everything, they exist in layers. So we've got two. Let's just say, for the sake of this example, we have two 10 gigabyte hard drives. These could be spinning drives. These could be SSDs. It doesn't really matter. We're just going to have two 10 gigabyte hard drives in the system. And we are going to be approaching this from a position of we aren't getting this storage delivered via a SAN or something that's already been made redundant and been made resilient. So we will have to take into account, how much resiliency and how much redundancy do we want in our data. And when we do that, we'll see a little bit later on. When we do that, we have to make a decision of how much money we want to spend on making the system safer, more usable, more performant, or having more space. We'll be using Ubuntu as an operating system. This is again for the example. We will be using Ubuntu in this class for assignments 2, 3, and 4, but we won't be installing anything for this lecture. In this lecture as an example yet. That will come later. But Ubuntu is what we'll use, and here's the Ubuntu logo. And then the end goal is, let's just say for the example, to install the Apache 2 web server, and this is the logo, it's a feather, whatever. That's just, we have hardware, we have the operating system, and we have software. So two 10 gigabyte hard drives, Ubuntu as the OS, and Apache as the software that we're going to run, just for an example. So let's kick it off with a single disk sort of situation. This is what most of you probably have in a laptop or maybe even your desktop. You've got one disk, whether it's one SSD or one spinning hard disk. It provides absolutely no redundancy, no resiliency, and the read and write performance are the same as is listed on the disk. So you read from the same disk, you write from the same disk. The write speeds and the read speeds are, 1x disk speed because we only have one disk. And sometimes because we request data to be read and also request data to be written at the same time, it has to do this dance of spinning the platter, aligning the read or write head, writing or reading the data, spinning the drive around, finding the next spot and everything. And there's centrifugal force that goes into all of that. I'll try to post a video to show that in Moodle, but there's some mechanical aspects for spinning hard drives that can make spinning hard drives very, very slow, especially whenever you have redundant or whenever you have concurrent read and write operations, potentially on either on extremely different sides or spaces on the disk. With no redundancy, literally anything bad will wreck your day, which will require you to restore from backup because I hope you had backups. There's no redundancy. There's no extra parts of data that are saved in more than one place other than your backups. Again, hopefully you have them. And if you've ever lost data, you'd want to definitely have good backups, or preferably do something with RAID. Now there's ways to mitigate this. There are ways to get an SSD something a little more predictable, failures predicted a little bit more effectively on an SSD, and in a laptop, SSDs are sort of the norm now. If they aren't, then you need to you need to replace your hard drive with an SSD because they save you on power, they save you on getting knocked around, especially for a laptop. You pick it up, you set it down. If it's online and spinning at the same time, you're really not doing yourself any favors for that. So one disk, you're asking for a bad day, you're going to get wrecked. You didn't listen to me, and I promise never again. And you want to buy some RAID. So we're going to talk about RAID next. So over the years, RAID has actually changed in its acronym. RAID used to be for a redundant array of independent disks, but since disks have kind of come down in price, it's actually also meant to mean redundant array of inexpensive disks. Either of those acronyms are appropriate because you get across what you're trying to say. The general idea of RAID is to distribute data over more than one disk, and you do this to achieve certain things, and usually not all at once. Though I guess you could. You could do all three of these things with more disks and more money. You distribute the data to increase capacity. You do it to potentially achieve some redundancy, which means you can lose disks. You can have disks fail, and you still don't lose your data. And you do it to increase performance, make your spinning drives act faster because you're reading the data or writing the data, reading the data from multiple places. The configuration for RAID disks, RAID arrays as they're called, or an array of RAIDed disks, are the disks in the RAID set. That configuration occurs on RAID controllers, which are typically hardware expansion cards that are PCI, PCI Express, or some proprietary daughter board that's installed in your system that your hard drives connect to, and then it connects to the motherboard somehow. RAID controllers are interesting because they're very performant typically, but they can be very expensive. And if they aren't expensive, there's a good chance that you're missing some critical feature. Perhaps you can only do RAID 0 and RAID 1, you can't do RAID 5 or RAID 6. For some people, that might be enough. A $40 RAID card just to be able to create a RAID 1 set of disks, that might be worth it to you. There are also just multiplier cards that add more SATA ports, add more hard drive ports, and these are really inexpensive, $20, $30. They might add 4 more ports on a different SATA controller, so you can just put more disks in there. And that's not all bad. You could increase your sort of spread your disks out horizontally, add more disks to the same system instead of adding more systems with the same number of disks. And if you're going to do that, there's this option to use software RAID, which instead of holding the RAID configuration on a RAID controller that has its own battery and has its own ROM and RAM and everything and is specifically dedicated to RAID, you could do it all in software. And this does have a little bit of, or used to have a little bit of a performance hit, but that's back when performance was really measured differently. We were really starved for performance. Now, software RAID doesn't really impact the system and is preferred in many instances because software RAID saves RAID configurations to each hard drive instead of saving it to a controller because you don't have one. The upside of that is if you were to lose a drive or if you were to lose a motherboard or a processor or something, you'd be able to retrieve your data by putting those drives in a different system, usually like a Linux system, and reestablishing your RAID. If you lost your RAID controller, though, the hardware card of your RAID controller, there's likely a chance you'd have to, or likely a requirement that you would have to get the same exact RAID controller or a compatible RAID controller in order to reassociate those drives with your RAID set, with your RAID configuration. And if you have a very expensive card, you probably don't want to buy it twice. So software RAID is available in a lot of cases, and if I post a video for establishing a software RAID, I will show you with software RAID instead of hardware RAID. So let's talk about different types of RAID. The very first type of RAID that we want to talk about is RAID 0. This is referred to as striping. And some hallmarks of this is there's no redundancy between the disks. So if you lose any of the disks in the RAID set, you lose all of your data. Now, realistically, there are options out there that may be able to recover some data, but chances are you'll be missing a lot of it, and it might not be useful. So for the sake of this class, for the sake of the exam, you lose one drive, you lose everything. Um, Capacity is the sum of all disks, so you will have the total. Think about it like n times space. So if you have 10 gigabyte disks and you had three 10 gigabyte disks, then you would have 30 gigabytes of usable space spread across three disks. Um, and then, of course, it increases performance because you can read from multiple places at once and you can write to multiple places at one time. And there's no need to mirror data. You're simply able to interleave and sequence your reads and your writes to spread out across multiple disks, thus achieving more performance. This, of course, is the math has to work out to where you are limited by the slowest spinning disk. So the slowest disk in your array, your RAID set, your RAID 0, if it's let's just say 500 megabytes a second, that's the slowest disk you have. That is the speed at which you can travel. But you can do that for each disk. It has to match, but you can spread it across disks. So it'd be, if you have three disks, 3 times 500 megabytes, effectively 1500 megabytes a second. It's a minimum of 2 disks for a RAID 0, though technically I think you're allowed to create a RAID 0 out of 1 disk. I'm sorry. Technically, a single disk is the same math and the same redundancy as RAID 0, but it's not a RAID set because you need multiple disks in order to create a RAID set. So just understand that like RAID 0 has a requirement for at least 2 disks in order to be a RAID set. But it's not restricted to anything. It's as big as you want to make it. If you wanted 3 disks, if you wanted 4 disks, if you wanted 12 disks, as long as you have the connections for it, it will work for you. So in this example right here, we have three 10 gigabyte disks, and we can see that every third bit of data on the rated disk is it's spaced out by thirds, right? So 1, 4, 7 correlate to the blocks of data on disk 1, 2, 5, and 8 correlate to the blocks of data on disk 2, and then 3, 6, 9 correlate to the blocks of data on disk 3, which means every time you're writing data in threes, 1, 2, 3, you can access and write to or read from 3 separate disks. So, and they're spinning and they're rotating and they're moving and they're storing data independently from each other, and it's all getting mashed back together on the rated disk side. Also notice that we have 30 gigabytes usable when we have 3 10 gigabyte disks, and we can see the math down at the bottom. They can be different sizes. The disks be different sizes. Say if one of those disks was a 5 gigabyte disk. However, it can't be you can't mix and match the size and achieve the maximum capacity. So it's n, where n is the number of disks, times the smallest amount of space. So in this case, we have 10, 10, and 5. It would just be 15, so 3 times 5 instead of 10 plus 5 is 25. So we'd lose 10 gigabytes of usable space, but we would have the performance, which would be n, where n is the number of disks, times the disk read or disk write rates. And it's the slowest write and the slowest read rate for the disk. Usually it's not something you do, but the math would work out that way. We talk about RAID 1. Now we're starting to get into a little bit of different territory where we're starting to see redundancy. There's a minimum of 2 disk requirements. I didn't put it on the last one, but RAID 0 technically needs a minimum of 2 disks to be a RAID set, to be rated. You need multiple disks. Minimum 2 disks for RAID 1. We refer to RAID 1 as mirroring because we are literally mirroring the data to 2 locations. It has n-1 redundancy, which means while we have a 2 disk minimum, we don't have a maximum. If you have space for disks, you can add disks to it. I'm sure there's some theoretical limit. We're not going to get into that though. N-1 means n is the number of disks. If you have 2 disks, 2 minus 1 means you could lose 1 disk. You have 1 disk that you can lose and still retain all your data. If you had 3 disks, 3 minus 1, you'd be able to lose 2 disks, and you'd still maintain a full-blown set, full copy of your data. This has really high read performance because it's able to read from the mirrored versions of the data, as many disks as you have. So it's n times the lowest read rate, which will give you higher read performance. There is a standard write performance though, because we have to wait for everything to sync up. So you write to the slowest disk, and then you have to write to every disk at the same time. You're waiting for those disks to come back. So just because you're writing to multiple places, that actually slows you down in comparison to like RAID 0, where you don't have to wait for everything to sync up and be mirrored. In the same way as RAID 0, and we'll see other disks, you'll be able to have more than 2 disks or more than the minimum of disks. In this case, here's an example with 3 disks. This can also have different size disks. So if we use the previous example of 10, 10, and 5, it will always be n times the smallest size though. And it's actually not going to be n times small, so it's going to be the smallest size. So ignore n times smallest size right here. That's a bad copy and paste on my part. So 10 and 10 and 5 will only ever be 5. This math is correct. This is not correct right here. The goal there is the capacity is going to be just the smallest disk size, right? We are increasing redundancy, we're increasing read performance, but we are not increasing capacity at all with RAID 1. So we're actually losing a lot of usable space. We're only getting really the smallest disk's amount of usable space. So if in this case 10, 10, and 10, it would just be a 10 gig usable rated disk. If it was mismatched sizes, it would be 10, 10, 5. It would just be a 5 gigabyte rated usable disk at the end. Read performance increases as more disks are added. So you could sum all of the disk read rates together, and that will add it together. Though really, it's going to be n times the slowest disk read rate, and write performance doesn't increase at all. You're still kind of barred by the slowest disk's write rate in this example. So we skip RAID 2, 3, and 4. They existed, but they aren't important. They aren't used. They aren't good. And some of them were just proprietary. And in some cases, I think in RAID 4 or in RAID 3's case, there were multiple implementations of RAID 3, RAID 4. We skipped sort of directly to RAID 5 because that's when things changed, when things got a little bit better. This isn't really in favor anymore, but we'll see why. This is called striping plus parity. This requires a minimum of 3 disks. It has a single disk redundancy. So no matter how many disks you add to this, it's only ever going to be a single disk's worth of redundancy. You can only lose a disk, but you can lose any disk in the RAID set. Any disk in the RAID 5 you could lose is fine. The way it does this is it spreads these parity bits across all of the drives. A parity bit in this case is just a sum of all the bits. So binary math, right? 0 and 0 is 0, 0 and 1 is 1, 1 plus 0 is 1, 1 plus 1 is 10, but we only take the ones place, so it's 0. So the goal there is if we lose any disk in the RAID array, let's just say we lose disk 2, if we say, bit 1, bit 2, the parity of bit 1 and 2, bit 3, bit 4, the parity bit of bits 3 and 4, parity bit of 5 and 6, and then 5 and 6, and we sort of stripe it like a barber pole. It's diagonal. If we lost disk 2, well, we lost bit 2, we lost the parity for 3 and 4, and we lost bit 5. But the great thing is we have bit 1 and the parity, so we have 1 plus x equals p, and then we have 3 plus 4 equals p, and then we have 6 plus blank, or x plus 6 equals p. We're able to construct the parity bits and the original bit information from the parity and the other side. That's why we can only lose one. We have to have 2 out of 3 components of the equation to reproduce the data. This increases read performance. Sum of n minus 1 the disk read rate, so it's effectively n minus 1 times the read performance. So if we had 3 drives, it would be 3 minus 1, 2 times read performance. That's what it averages out to. But it does decrease the write performance in RAID 5 because we're completing a lot of operations for every write. For every write, we have to check the bit of data. We've got to compute the parity bit. We have to remove the old bit of data, and we have to write the new information. So that's like at least 4 operations for every write. And depending on the implementation of RAID 5, it might be even more. Performance is impacted during what's called a rebuild. A rebuild is if you were to lose a disk. Say we lost disk 2. If you lost disk 2, then you would, let's see, mechanically, you would take the drive out of the hardware out of the computer or out of the RAID set. You would put a new physical new drive back in that would be compatible, and then you would allow the rebuild to occur. The rebuild is going to be the operation of creating the parity bits that you can create and copying those over, and then reconstructing the original information and putting that on that disk as well. But during this process, all of the disks in the array are super busy. You've got all of your disks, your original disk that didn't fail, that are being used to reconstruct the data that was lost during the failure. And that new hard drive that you put in there is being bombarded by all this new information. Potentially, it's 100% capacity of new information, even zeros, right? 0 plus 0 equals 0. It's even putting empty space back in there because it's part of a RAID. It has to match. So the general idea there is, make sure it's a good disk, not some old disk, because it might just fail again during that rebuild. And performance is going to be significantly impacted because there's going to be a lot of reads on the disks that remain and a lot of writes on that new disk that you just put in. Regarding total space, we're going to see an n-1 times space increase. So the goal there is, because we have a single redundancy, we have to take one disk's worth of capacity out because that's effectively dedicated to parity. While not all the parity is not on one machine or on one hard disk, and it's striped and spread across, it's one disk's worth of capacity. So we see that we have to take one disk out of the math there. So if we have three 10 gigabyte disks, it's going to be 10 times 2, which will be 20 gigabytes usable. So we gain a disk of redundancy. We gain increased read performance, and while we lose write performance, we do get that reusability or redundancy, and we get a small, a third capacity. In this case, a third, one disk capacity, diminished capacity, which isn't a bad trade-off. So, and then for the math out there, this is sort of if you were to fill in parity bits with just dummy information, that's what you would get. You could also expand this past 3 disks if you'd like. There's no restriction. Again, maybe some theoretical max, but there's no restrictions. I've had six drive RAID 5s and no big deal. Again, moving forward, RAID 6, which is dual striped plus parity. This is a minimum of 4 drives. We add a disk redundancy, so 2 disk redundancy, and then we add an additional parity bit. We still use the original parity bits idea from the previous. We distribute it amongst the disks, so every third and fourth disk will be parity, sort of staggered parity, like this. So disk 1, disk 2, this will be the parity bit 1 from disk 1 and disk 2, and the second parity bit from disk 1 and disk 2, and then we'll see 3, and it'll just be staggered the same way. We use the first parity bit as just the XOR, just like RAID 5. It's math, right? 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. The second parity bit is a little bit more it's a little more complicated, and I recommend, if you wanted to look at the math, if some of you are math majors or double majors, you might want to go to the wiki page and pull that up, because it's calculated via register shifting, XOR operations. It's a little more complicated, and if you lose both original disks, you should be able to recalculate those disks information with the parity bits. So if you only had parity 1 and parity 2, you will be able to create original first information bit and original second information bit from those. So it had to be different. You can't just store a copy of the parity bit. Because we have now effectively used 2 disks worth of, again, it's staggered, but 2 disks worth of capacity for parity information, the space is the maximum size, usable size, is going to be space times n-2, where n is the number of disks. So if we had 4 10 gigabyte disks, that will be 20 gigabytes usable, because we'll only take 2 disks into account. And finally, RAID 6 is recommended over RAID 5. And this is for a few reasons. We talked in RAID 5 slide about how during a rebuild, performance will be diminished. Well, in addition to performance being diminished, your RAID array is incredibly volatile. It's being taxed hardest it's ever been taxed. It's being asked to complete so many operations, and assuming that you've built it all at the same time, the disk that failed or the disks that are still operational are just as old, maybe even from the same batch of disks as the disk that has failed that you are replacing. So, in addition to them being old, you're also asking them to work 100% to rebuild the new information. There's no better time for your disks to fail than when you're rebuilding an array, rebuilding a hard drive in an array. So because of that, RAID 6 was sort of envisioned where, with respect to adding more redundancy, that's always good. Typically, the performance is sort of the similar sort of game, except instead of -1, it's -2, and then also, considering you have multiple disks redundancy, and it's very unlikely, just statistically, to lose two disks at once, and required to rebuild two disks at one time, you can lose one disk. You can begin rebuilding it. If you do lose another disk, that's okay. We were always able to lose two. It's just increased the sort of the safety net for RAID 6 because RAID 5 didn't really have one. You lost one disk, okay, and during rebuild you lose another one, your data's gone. RAID 6, if you lose a disk and you're rebuilding and you lose another one, well, chances are you can, you can limp along a little bit. And it's statistically just not very common for that to happen. With RAID, we are able to combine RAID into RAID combos, which are just RAID sets in and of themselves. It's a RAID set of some RAID sets of some disks. So I copy and pasted the image from the RAID 1 RAID 1 up here. So these are two RAID 1 sets. So in the hard drive, in the hardware, we would have four 10 gigabyte disks, right? So disk 1, disk 2, let's just say disk 3 and disk 4. I know it says 1 and 2, but that was because I didn't want to make this diagram again. And these are rated into RAID 1s of 10 gigabytes. So we have 10 gigabyte RAID 1s, two of them. Let's just say RAID 1A and RAID 1B. 10 gigabyte RAID sets. We can then put those into a RAID 0, and we can see that RAID 0 will every other bit of information will access the information on RAID set A1, or yeah, 1A rather, and every even bit will be accessed on RAID 1B. And this is called a RAID 10. It is a RAID 0 built with RAID 1s. The great thing is we get the redundancy of RAID 1. We can lose disk 1 in both RAID sets, and we're fine. Or disk 1 and disk 2 in RAID set A and then RAID set B. Or any one of these disks, we lose one of them, and we can lose one of these as well, and we're good. So we can lose, as long as they're in different RAID sets, two disks. And we get the write performance of RAID 0 because we're able to read and write to multiple disks at once. Now, admittedly, we're slowed down by RAID 1's need to mirror data, but we really don't feel that as hard as good as we feel the increase in performance over here. This is a RAID 10. It's really common for databases or high performance services. You need resiliency. You don't mind having, in this case, half of our physical storage. We would normally have 40 gigabytes worth of disks. Instead, we have 20 gigabytes worth of disks, and depending on what disks go out, we have two disks of redundancy, and we have higher performance than RAID 6 because of the write performance trade-offs. So RAID can be comboed, and it's not just RAID 10. You could make RAID 55s. You can make RAID 50s, RAID 60s, RAID 61s. You could build this however you want as long as you have the disks. And I encourage you to sort of think about that because on the exam there will probably be a question about building certain RAID combos or asking you capacity information about RAID combos, and you need to understand how to build those. Okay, so currently, if we were to look at this in a RAID 1 sense, we could look at our hardware level with our 10 gigabyte hard drives. The disks are going to be disk 0 and disk 1. They are 10 gigabytes. We have put them in a RAID 1 disk. So the operating system will see one RAID 1 disk, which is just 10 gigabytes usable. And then we'll install everything on top of it. I said in the previous slide that this isn't coming from a NAS or SAN in this example, but just understand that it's possible that whenever you get storage in an enterprise scenario, that storage may already be redundant and resilient, and putting RAID on top of resilient storage is sort of a waste, right? You're wasting more storage and you're not getting any performance because it's already resilient on the storage side. So in this example, we are assuming our 10 gigabyte drives aren't rated already, aren't coming from some NAS or a SAN solution that is giving us resiliency out the box. But if we knew that that was the case, we wouldn't really have to do RAID. There's no reason to. So from the operating system standpoint, we will see a single 10 gigabyte RAID 1 disk that we'll look at as multi-device 0. And that's just how Linux prefers to look at rated disks. Whenever we have RAID is a low-level sort of operation. We are that's before the operating system is installed. The OS is installed on top of it, and in order to do the installation of an OS or to have files or to put data on a disk, we have to partition the disk, which is effectively splitting any usable space on a disk, whether it's a RAID disk or a stock single disk hard drive. We split that usable space up into regions so that we can put data, so that we can install or format that region with a file system. This is useful for separating data. That's commonly what it's used for, but it's also useful for putting multiple OSs on the same disk, which is really just separating data. Disks have to be partitioned before use. It's a requirement. It used to be that we were barred by 4 primary partitions. So we're still barred by 4 primary partitions. This is a legacy restriction based on the master boot record structure of the past. But it used to be we could only ever have 4 partitions and that was it. Almost immediately, within a year or two, we were like, well, we need more. But we had already built it into MBR that said 4 is the max. We came up with a way to put logical partitions held within something called an extended partition, which is effectively a primary partition, and I know it's nested, but effectively you take one of your primary partitions, you declare it as an extended partition, and then you can install logical partitions inside of it. And the logical partition acts like a regular partition with in almost every sense, except you can't boot the system from a logical partition. So typically what you'll see is you install your boot directory on a primary partition, and then everything else can be on a logical partition, no big deal. And those are relatively unlimited. Again, I'm sure there's a theoretical max, but you'll never hit it. It's just ridiculously huge if it is. And you can install everything on logical partitions. There are a lot of tools to accomplish partitioning your disk. Installed in Linux is usually fdisk. Some versions of Linux have gparted. And then there's Partition Magic, Partition Wizard. You can partition things on OS install, which is typically how you do it. And that's how we'll be doing it in our LVM setup. We'll be partitioning things halfway sort of in the OS and then separately during in the OS install and then separately during inside of the operating system. My advice is you want to do this right the first time, because doing it wrong and then trying to fix it later is a big pain. You might lose data. You might put data on there and then it might just be abandoned. Like you might not be able to get to it anymore, which is effectively data loss. It's really difficult to repartition the system once you've already started using it. And if you screw it up at the beginning, start over. You're at the beginning. It's like no better time to start over than at the beginning. It's really easy to mess up partitioning disks because it's a mindless task sometimes. You get into this flow of partitioning things and splitting things up, especially if you have a lot of them and you're not doing it in an automated fashion. Just understand that there's you need to be a little diligent because this is the foundation. You're pouring the concrete to your system right here, and it's important to not mess it up. You want to plan your partitioning table. In this class, I'll tell you how to partition what I'm expecting and what I want, but you might need to partition things differently depending on what type of problem you're solving. Perhaps you need more tiny partitions than than big partitions. Maybe you just need one big partition. It depends on the type of problem that you're trying to solve. After we partitioned our system, we have to install a file system on the system. I have an analogy, and I've been working on it for years, and I'll try to remember it. If your hard drives or your RAID set is like a big warehouse. You have a big giant empty building. You open the doors, you go in, and there's all of this space. And you have a stack of paper in your hand, and you go, well, let me fill the entire place with this paper. Let me just throw it on the ground. And later, when you're like, I need to find this specific file, you look around and there's just files on the ground. You have no idea. There's no sorting. There's no method to this madness. So you say, okay, well, let me do this. Let me build little rooms in this warehouse. That's partitioning. You're partitioning the warehouse into rooms. So then you go into a room, and then you take all the files that are supposed to be in that room and you throw them in the room. And then later you come back to that room and you go, I need to find this file, but there's still files on the floor. You know the file's in this room, but the room is still just not sorted. So you go, okay, well, this isn't working either. A file system is as if you are putting filing cabinets in that room. And then you put the files in the filing cabinets. Later you come back and you open the filing cabinets and you're like, here's the file I need. File systems control how that data is stored, how that data is accessed. It can be file names and directories and metadata and timestamps and permissions. All of that is held within the file system. And depending on the underlying file system, you may have certain restrictions. You have space restrictions. You have block restrictions, which is a big deal in the storage world. That we may talk about in sort of a catch-up episode or a catch-up lecture. Windows typically has now really just NTFS and REFS. Those are it used to be NTFS was the number one. That's the one we use all the time. Now I think REFS, the resilient file system, has sort of taken over in Server 2019, and I believe Windows 10, maybe Enterprise, maybe it's still NTFS. But legacy, you've got FAT16 and FAT32, and then if you wanted to do some cross Linux or cross Mac sort of file systems, exFAT, extended FAT file allocation table, is a worthy file system. You can't boot from it, but you can read it as an extra partition, as an extra file system. In Linux, there are 50, I guess, maybe file systems. You'll see it when we partition or type an LVM partition, because you'll see all the different types that fdisk allows, and there's more than just that. But ext2, 3, 4, ZFS, XFS, JFS, unless otherwise noted, we'll be using XFS for this class. But there's other file systems that you could totally use, depending on the type of problem you're solving. And then, think about anytime you need to store data, whether it's a USB drive or in this case CD or DVD or Blu-ray, there's file systems for those as well. And file systems for CD and DVD are ISO 9660. For Blu-ray, it might be similar, it might be different. But if you need to manage file names or directories or just any data at all, you need to have a file system. And then we talk about operating systems. Operating systems are installed on top of our file systems. So for Windows, I'm not going to touch on this long because everyone's dealt with Windows. Everything is typically underneath your C drive and in a few places. You've got your program files and your x86 version of your program files. Then you've got your users directories where all your users are. Then you have your critical Windows directory with System32 and all of that stuff. If you delete any of these directories, chances are you're going to have a bad time. Linux is a little bit more verbose. We've got a lot of directories, a lot of volumes underneath the root volume. So root volume is just slash. We call it root, but it is denoted by a slash, and then everything is from the root. So instead of c:/, you'll have like c:/ users. You'll have in this case slash home slash etc. We call it etc /dev/bin/boot. So it's slash is, if you just go to the slash directory, you'd be at the root of the file system, and everything is underneath the root of the file system. So everything goes underneath /root. /boot is used for files to boot the OS. This has to exist on a primary partition because it just does. Those are the rules. /bin are for binary files. These are for commands and shells that are really important to the system. You don't want to delete them. /dev is a virtual and physical device sort of moniker, as where everything that the system would recognize is. /etc. These are config files for a lot of extra things, or a lot of things installed in the system, but also optional files that are installed, optional binaries. We'll typically put config files in the etc directory. /home is for user directories. /lib is for system libraries, which are common shared libraries. /media isn't necessarily forced though, for CD-ROM, USB, floppy, things like that, removable drives and devices. /mnt, that's a location for mounted directories and devices. So if you're mounting something from a network location, or even potentially from a media location, you can use /mnt to mount that. And that's a hard and fast rule. It's not a requirement or technical constraint. /opt is an optional application directory. /proc is for information regarding processes, so you could actually see traces and everything going on in real time. /sbin are for system binary files. This is sort of like /bin. There are just extra things in it. /tmp is a temporary files and directories location. Again, hard and fast rule, not a constraint. You can put files wherever you want in Linux. It's so open-ended it hurts you sometimes. /usr, user. These are user installed programs, similar to /opt, but more pointedly towards a given user. And then /var, these are variable files, log files, and also the default web location. So there'll be /var /www /html, public HTML, and that'll be like where if you installed a web server on a system, that's where the base of the web root would be. When we are talking about file systems, we have to make decisions. We've got our partitioned space. And we have to decide how we are going to split up that partition space. We could use one file system for root, and that's easy, but it might not be the best thing to do. And I didn't touch on this in the file system area, but Linux has something called swap area. Swap area or swap space is sort of like virtual memory for Linux. You don't need it. You may need to define it, but you don't necessarily need to use it. In fact, if you start using virtual memory or swap, things are going to slow down dramatically because you're actually using hard drive space as RAM. You don't want to do that. This is only a countermeasure or a measure if RAM filled up, all of a sudden, and you needed to continue to operate, albeit slowly. If we use a single large file system for the root, in this example, this little screenshot, I have a 9 gigabyte partition, and it's all files. The entire file system is mounted to root. I've used 1.3 gigs of it, and I have 7.8 gigs available. Everything that goes onto my system will consume that 9 gigabytes of space, that 7.8 usable space. Rogue processes and users can fill up their home directories, eat my disk space, fill up all the disk, and when no space is left for critical processes, the system could crash. The system might not be able to let me log in to try and fix it. And literally anything could do that. Users could upload data to their users' home directories or a web drive or something, and a website on the server. And if I run out of space, I run out of space everywhere. So a single file system is maybe not the best. So you can split it up. You can create multiple file systems. In this case, I have 5 file systems minus the one for swap, because we can't see that one, but I can see that, okay, my root file system is now approximately 2 gigabytes. It says 1.9, round up a little bit because there's always some fall off with Linux. So a 2 gigabyte root file system, a 1 gigabyte user file system, a 100 megabyte boot file system, a 1 gigabyte var file system, and a 2 gigabyte home file system. And then some amount left up to swap that we really don't see and we don't care about right now. So the cool thing about this is, while it does take a little bit of doing to set up, the individual file systems can fill up, and it doesn't affect other file systems, right? So as long as the root file system doesn't fill up, every other file system can fill up, and I could still log in and I can still do my job cleaning it up and everything. Which is really, really, really convenient, especially that home directory. Having that at 2 gigs and separate, that means if users are negligently adding things to their home drive and they fill up 2 gigs, it doesn't brick the system, it doesn't slow down, it doesn't prevent the web server from working or system, files from updating or anything like that. So it's important to consider that you should split out your file systems. This is working on this is a better decision than a single big file system most of the time. In either case, if you decide to add space to a file system or if add space to a partition, let's say you've formatted it as a file system on your partition, and you run out of space and you need to add more. You you can add more. It's just a little bit of a pain, and that's where LVM comes and saves us. So let's analyze this screenshot for a minute. I could see this is the first example of a single large partition for a root, and then an amount, a 1 GB partition for swap. So we could see that this is approximately 9 GB of primary partition that's bootable, that is formatted as XFS. And this is, if I go back 2 slides, that's what this is referring to. And then we can see that there's some padding that's free space, about 1K of padding and then 1K of padding. And then we can see in the second example, with this multiple sort of example right here, we can see that there's 1K of padding, 100 megabyte bootable partition. Again, these are ext4. Don't pay attention to that too much. There's another 1K of padding. That's just to make sure that we can start on a good number, not a decimal number. We have an extended partition that then contains, it's a 7 gig partition of extended stuff, but inside that we have a 1 gig logical partition, a 2 gig, a 2 gig, some padding, a 1 gig, and a 1 gig. And then at the very end, we have an amount of free space. We have about 3.6 gigs or 3.5 gigs, or it may just be 3 gigs, I can't remember, of free space after line 9. I can't go down there because the presentation controls will pop up. But so if we wanted to add that free space, we have to do some finagling a little bit. We have to make sure that free space is adjacent to our partition that we want to resize. We effectively resize that partition and consume that free space, and then we have to make the free space sort of usable for us. So in this case, we'll resize partition 2. And this was our multi free space or multi file system example. We resized partition 2. So originally it was 6999 megabytes, so 7 gigs extended. We resize it, and we're going to resize it to be 10.7 gigs or whatever. And that's effectively taking the, I wish I could move this. That thing. If you look at the bottom, it says 3638 megabytes under the size column. That is free space. So we're going to create and add that 3.6 to the 71, and that's where we're going to get this 10.6 gigabyte resize. So after the resize, we've got a 10.6, and now there's just like 37 megs of free space down there. And notice there's 2 lines. There's the 37.4 megabytes of free space, and then right above that there's that 3600 megabytes of free space again. But notice where that, notice right here, the start and the end. Partition 2, which is the extended partition, it starts at 101 and goes to 10.7 gigs. Look at the end of that first line of free space down there. It ends at 10.7. So what we've done compared to this, we start at 101 and we end at 7100, and then that free space started at 7100 and ended at 10.7. We moved to that 3.6 gigs of free space into this extended partition. So the first step was we moved the free space into an area, into a place where we can start using it. The next thing is now we need to move an amount of free space adjacent to a partition that we want to extend. So for instance, if we wanted to extend, let's just say 6 is /home, I think it might be. If we wanted to extend /home, notice it starts at 1101 and ends at 3100. We would have to move an amount of that 3600 megabytes of free space underneath, like between 6 and 7. We'd have to move it around, and that's problematic. That's hard. I'm not going to show you because we typically don't do this anymore. And I was just showing you that you have to resize it. You have to look at the starting numbers, and there's sectors. Whenever you're doing that, you have to change it, change sector math, and add sectors to it to kind of sandwich that free space between 6 and 7, so you can then increase the file system from the partition from 2 gigs to 3 gigs. Let's just say, for example. So let's move on because I don't want to spend too much time on that. We're already at about 50 minutes on this presentation. So currently we've got redundancy via RAID 1. Those disks may be redundant already. The operating system will at least need a boot volume, a data volume, and a swap volume. So what we can do is we can partition those into smaller chunks and RAID those smaller chunks. So instead of RAIDing the entire disks, what we can do is we can chop up the disks, these individual disks. So these are the physical hard drives in pink. We could chop them up into 3 separate things. So 100 megabytes, 1 gigabyte, and then the remaining, which is like 9.9 gigabytes. We'll give 100 to boot, 1 gig to swap, and then the remaining space will be installed to root. Again, we don't want to do this, but I'm working on a progression here. So there will be 3 RAIDs, right? There will be software RAIDs for RAID 1 for the boot drives. There'll be RAID 1 for the 1 gigabyte partitions, and then RAID 1 for the 9.89 partitions. And that's kind of how it would look, right? We would install Ubuntu on the slash drive, which is 9.89 gigabyte RAID 1, and then this would be a 100 megabyte RAID 1 and a 1 gigabyte RAID 1. And that's just showing that with software RAID, or even with I guess a controller-based RAID setup, you don't have to RAID you don't have to RAID the you don't have to RAID the entire disks. You can cut them up and then RAID the partitions with software RAID. So RAID's really important, right? But we know that the single large root partition thing is bad. We don't want to do a single large file system. So we want to swap that around to use the multiple partitions and multiple file systems. And we want to use it as much as possible within reason. I mean, we don't want to get really crazy. So this is the same amount of disk space, but we've drastically changed the partitioning layout, right? Preferred though, right? So we have 100 meg for boot, we have 1 gig for swap, we have 2 gigs for home, we have 1 gig for var, we have 500 meg for opt and 500 meg for user, we have 1 gigabyte for the root partition, and then we're still left with about 4 gigabytes left. And I always like to leave some free space in my system because you never know what you're going to need later, and you want to be able to expand a little bit. You don't want to give someone terabytes to use, and then when they use it, you go, well, I guess we'll have to buy another hard drive or somehow extend this. And these are all individually, multi-devices. In fact, I realize that this should be MD 2, 3, 4, 5, and 6. So my MD devices are off by 1 right there. I'll try to fix that. But yeah, so that's good. So why do we want multiple file systems? Let's kind of go back to that because it's a big important concept to understand. Computers are far from perfect, and when I say that, I mean that the hardware can fail and software can become corrupt, and it can do it like slowly, like over time, but it could also do it very all of a sudden. And when it happens, you don't want to be stuck with a completely bricked system. It's okay if you've got like one system, like one file system that's not working. It might be just statistically, it might not be a very critical file system, as in your data is not gone. You may have to reinstall Linux, but that's not the big deal, right? Not a big deal to reinstall Linux. It is a big deal, unfortunately, to try to reconstruct data. So hopefully your data partitions are good, or your data file systems are good. With multiple file systems, problems that problems can only affect that file system. It doesn't bleed over. It might bleed over in the sense that if the program that you're running is installed in a file system and the data is written to a different file system, if one of those fill up, it might stop the program from working correctly. But what I mean is that the data on a non-affected file system is just that. It's non-affected. So that's good. But big problems can still affect everything, right? If you have a RAID controller failure or a misconfiguration or a power failure or a hard disk failure or a motherboard failure, that's still going to impact your data, potentially corrupting the file systems. That's still going to create downtime and trigger an event. So you want to watch out for those. It's not multiple file systems in RAID don't fix everything. It's just a precaution that you can take. So free space can be allocated to wherever you desire, right? Only if it is directly adjacent to the file system, though, and that's what I was showing in the previous slides, where you have to move that free space into a partition if it's an extended partition or a logical partition. Then you have to segment that free space. You have to move it adjacent to the data that you want to increase the file system on, whatever file system it is. That may require moving file systems around. And in addition to not being fun, a lot of things can go wrong with it because you have to compute math, you have to compute sector offsets, and ideally you want to use a program to do it. You want to use something that's a little more high level to do all the low level stuff. You want to use something like gparted or partition magic. You want to do something that will automatically figure it out for you. You don't want to do it manually. So based off of the latest partitioning table that we had designed in this theoretical example, Ubuntu is distributed across all of these relevant file systems. They act independently from one another. So if you have a service or some program that depends on multiple file systems, they could still totally be affected. So you wanna watch out for that. But even at this level, right? Even with this, it's still tedious if we wanted to add free space to say /home or /var, because that free space is at the way end of the partitioning table. We'd have to move it all around. Thankfully, we have something called logical volume management that will help deal with all of that. So it's really important to it's good to understand where we came from, but it's also really important to understand this is kind of where we're at. Logical volume management, or LVM, this is what we will be doing. This is assignment 2. This is the big deal. This allows for resizing file systems without directly adjacent free space. We're able to allocate data or allocate space to a file system without it being anywhere near the file system. It just has to be in the same group, the volume group, and we'll get to that in a little bit. Logical volume management also allows for mirroring and snapshots, so you can mirror a logical volume to another place on a hard drive or another volume completely, and you could also take a time-based snapshot that you can immediately roll back to should things not go how you want them to go. For instance, if you're trying to upgrade something, you can take a snapshot before you even attempt the upgrade, try the upgrade. If everything goes well, you can remove the snapshot. If everything does not go well, you can immediately fall back to that snapshot, and it's as if no changes were taking place, which is really convenient. Big thing changes can occur when the file system and the overall server is online. No restarts are necessary, which are sometimes necessary whenever you're dealing with conventional, more traditional non-LVM management, LVM paradigms. You can span multiple physical volumes. These can be regular hard disks. These could be RAID disk. These could be a mix and a match. This can quite literally allow you to just throw another hard drive in and extend data onto that hard drive. Now you're still on the hook for resiliency and redundancy as delivered by RAID, right? LVM is not intended to replace RAID. It's a complementary sort of system. And there's a rule: /boot cannot exist inside of a logical volume. It has to be on a primary partition inside a conventional volume. And the reason for that is the instruction sets, the rules for how to use logical volume management are within /boot. So you can't open LVM and deal with LVM when all of the instructions, when the guidebook and the manual is all inside of /boot, and /boot is inside of LVM. So it just doesn't work. So /boot is really the only thing that has to exist on a primary partition outside of LVM. LVM is primarily intended as an alternative to other types of conventional partition management. It's pretty much in every Linux distribution I've seen, LVM2 is included. Windows doesn't have LVM, and it sucks. I really wish they did, because LVM is awesome. And Mac OS X had something called core storage. I don't even know if it's supported anymore, but it touted LVM, but it's not really like the LVM we're talking about. The previous concepts still apply though, right? So you need a resilient and redundant base, whether that's a RAID 0, RAID 1, or RAID 5, or RAID 6, depending on the problem you're solving. And it's good to have multiple file systems. You just put those file systems inside of an LVM container, and we're going to get some nomenclature out of the way so we can explain that. So physical volumes, PVs, these are block level devices that store the logical volumes. Physical volumes are things like RAID sets, RAID arrays, hard drives, anything that the data is going to be at a really low level, at a block level stored on. So technically, it could be USB drives or some other type of block level rewritable medium, iSCSI, a network drive, something like that. That's block level, not file level. It has to be block level. So NFS, SMB, those are out. Technically, NFS I think could be block level. SMB is definitely out. AFP definitely out. iSCSI in though. Then you have PEs, physical extents. These are the minimal size allocations on a physical volume. So this is the smallest amount of size that a physical volume can, or a physical extent can be. So it's the smallest amount of data that you can store on a physical volume. Which mean, and it's really just a mapping, right? Where it's how many physical extents are you going to allocate for something. So the default is around 4 megabytes, I think. So if you had a 4 gigabyte physical volume, then it's got about 1,000 physical extents on it if they were at 4 megabytes. Again, that's some quick math, but you get the idea. It's a mapping. We're going to see how that works out later. Then we have logical volumes, LVs. These are areas on physical volumes that hold file system data. This is where we will install our file system and thus our operating system and our files. Logical extents are a one-to-one mapping of, well, not necessarily a one-to-one mapping, but a mapping between the physical extents on a physical volume and the logical volumes. And then volume groups, VGs, are the collections of logical volumes and physical volumes. So it sort of tells the system what physical volumes a logical volume can correlate to. And we'll see that now. So logical extents map to physical extents in, like, most of the time, non-contiguous ways. Contiguity meaning they are adjacent to one another. In fact, we look at, say, this the resulting volumes. Let me just get that out of the way. The resulting volumes, they don't care where the data actually is on the physical volume because it's an abstraction layer. It's meant to be non-contiguous. It's meant to just tell me, it's an index. Tell me where that data is. Point me in the right direction, and I don't care where it is. I know where it is. I don't care if it's sequential. It probably won't be sequential. It'll be spread out everywhere, and that's okay. So in this case, we've got our root file system installed on the root logical volume that's made up of an arbitrary amount of logical extents that correlate, and I'm not going to move it down there too far because the controls will show up, but it'll correlate to the physical volume in the root volume group. And in this case, it's correlating, it looks like blocks 1 and blocks, physical extents 1 and 3. Okay, they're not contiguous. There's some space between there. The slash home file system is installed to a separate logical volume, home logical volume. It too has 2 logical extents in it. These are just arbitrary. These could be 8,000 logical extents, physical extents, doesn't really matter. They point to blocks 2 and what is it, block 6 on the physical volume, physical extents. So they're really far apart, not linear, not linearly. It's not linear. It's not like it's you skip every other one. And this scales. I mean, it could be you skip 5,000 blocks and then you skip 5 blocks, and it doesn't really matter. The point is, we are able to, whenever we're on our file system or whenever in our logical volume, these logical extents are in order. They're in sequence, and they'll reach out and grab data across multiple physical volumes if need be. They just have to be mapped. Logical extents need to know where the physical extents are, and logical volumes need to be in the same volume group as those physical volumes that the data is stored on. So let's look at a little bit of a different schema. This is approaching really. Actually, this is good. This is a good example, I think. So we have a physical volume. This is a 10 gigabyte multi-disk 0. So this could be a RAID 5. This could be a RAID 1. It's rated. We know it's rated because the multi-device thing right here. So it could be even a RAID 0, but probably not. Let's assume it's a RAID 1 disk. I say it right there. So we have to have a conventional XFS partition. It's 100 megabytes for our boot, and then everything below this dashed line is meant to be a volume group for root VG. Root VG is 9.89 gigs, so it's everything else of this 10 gigabyte disk. And inside of that, we see that we have a root logical volume, a var logical volume, a user, an opt, a home, a swap, and anything that's not specifically named here, these file systems slash user slash opt slash var. So for instance, slash etc slash bin slash sbin, they all fall underneath root right here. So slash bin slash etsy slash sbin slash temp, they're all underneath root right here. But we can see this root logical volume is 1 gigabyte of the root volume group. At the end, we've got some free space that's just kind of hanging out, and it's 2 gigabytes of free space or something, almost 2.9, almost 3 gigabytes of free space. The great thing about that is we're able to move this free space around. If we wanted to add another gig to root logical volume, we can totally do that. We can do it really easily, in fact. It's something called the LV resize command. They also have LV extend, I think LV extend and LV reduce. You never want to reduce the size of a logical volume. I'm going to say that it's you can totally do it, but it's frustrating if you do it the wrong way. So we're only going to be talking about increasing the size. So when you want to extend a logical volume, if there's free space in the volume group, right? So not in the logical volume, but in the volume group. So this is the volume group, the sort of lightly shaded area. We have 3 gigs of free space down at the bottom. Provided there's free space in there, you can extend any of those logical volumes in that volume group. So it would be LV resize, and this is a lowercase l. It capitalized it accidentally. LV resize dash capital L is going to be a way for us to just say plus and then a number and a unit. So plus 1G is 1 gig, plus 1.5G is 1.5 gigs, 100M, 100 megs, and then the logical volume path. So this would be the absolute path to that logical volume that we want to extend. So example, here, if we wanted to add 1 gigabyte to the root logical volume, it would be something like LV resize dash capital L plus 1G. This is 1 gig. We want to add it. That's what that plus dictates. And then the volume path would be slash dev slash mapper slash root VG dash root LV. And that will add 1 gigabyte to the logical volume. Now, we still need to resize the underlying file system, and we could do that one of two ways. If we would have added, before this dash L, if we would have added a dash lowercase r, then that will run the resize for the file system as well. So it will increase the root file system to 2 gigs as well as the logical volume. If we forgot to do that, though, we could use the XFS grow for an XFS volume or resize 2FS for the EXT volumes. And then there's relevant commands for JFS and so on and so forth. So it's just important to know that we will have to resize the file system because we're enlarging the logical volume, but the file system is still tiny inside of it. So that's always something to consider. Some interesting things about logical volumes. Volume groups and logical volumes can span multiple physical volumes. So what this means is when you run out of space, you can just add more hard drives, add more physical volumes. They can even be completely different types of physical volumes. I wouldn't recommend it. I'd try to keep them all the same, but I wouldn't mix hard drives and SSDs with the same logical volume, because some of your data will be really accessible fast and some of it won't be, and you won't really know how to do that. You'd want to make an SSD tier of logical volume partitions and then a regular hard drive tier. You can associate new physical volumes with existing volume groups, so you don't need to recreate volume groups. And you can extend logical volumes that are already made into that new space just by adding more space to the volume group. You can map logical extents to multiple physical extents, which means you're writing the same data to multiple places, which is effectively mirroring the data. But again, it's not meant to replace RAID like it is. I can't stress that enough. You still need RAID, because even though you mirror the data, if you mirror the data to a logical volume on the same physical volume, then congratulations. When you lose your hard drive, you still lose the mirror data. There's reasons to mirror the data for other reasons. You might want to be able to, mess with data in a vacuum or put the data someplace for safekeeping, out on a different physical volume without using RAID, sort of like a really quick backup scenario. So let's ask some questions and answer it, right? So what if all the space was used on the RAID that we created, that MD0? We could add another hard drive into the system, or create a new RAID set, create another MD1 or RAID 1 for MD1, and then we could add that data into the existing physical volume or the existing volume group, and we can then extend our logical volumes. If we wanted to add a new file system called /data, we actually do this in assignment 2. This is part of the assignment. We can create /data inside of a data logical volume, or maybe even inside of a data volume group if we had more disks that we wanted to expand that into. LVM will do all that for us. And finally, for the final slide of this presentation, I know it's a long one, let's look at sort of a more comprehensive example that is really, really close, if not exactly what assignment 2 will be. And again, if this, you want to check assignment 2's requirements, you want to read over them very specifically, because I think I modeled assignment 2 off of this, but I may have changed it up. If we look at this being a separate hard drive or a separate RAID disk, this is a separate rated disk, and this is a separate rated disk, right? So the gray, the orangey yellow, and then the red is separate disks, separate RAID ones, right? So we have 10 gigs, 10 gigs, and 5 gigs. It's conventional, it's possible for us to partition things in a way where, 5 gigs of RAID of root volume group is on MD1. Almost 10 gigs of root volume group is on MD0. There's still some free space inside of that. We have this data logical volume and /data drive down here that's 10 gigabytes, but is spanned across a 5 gigabyte RAID 1 and half of a 10 gigabyte RAID 1. So, and the great thing is the OS doesn't, it's aware, it knows about it, it has to know about it, but as far as the user is concerned, just a user that's putting data in /data or a program putting data in /data, it doesn't know, it doesn't care. It looks at it, is able to just put the data there, and it is spread across, in this case, potentially 4 physical disks. If we're using two disks in RAID 1, 2 disks in RAID 1 over here. 4 rated disks. Same thing with this. We only had, we used the rest of the free space here. There's 3 gigs of free space to increase our thing right here. So we needed to increase these another 1 gig from our previous example. Well, we were able to do that. We were able to take 2 gigs out of this 5 gigabyte half of this disk and add it to add 1 gig logical volume on this disk and 1 gig root logical volume on this disk, and add it to the var and the root file systems. We were able to get 2 gigs out of those. So 1 gig over here, 1 gig over here, add to this 1 gig and this 1 gig. The file system doesn't care. The underlying file system, it just knows my data is going to sometimes go over here and sometimes go over there. And the great thing is, it's not really a performance hit anymore. It used to be on slower disks and on slower systems, it was performance hit, but not anymore. Things have gotten kind of fast. So this is, take a minute, try to understand this image specifically. Go ahead and look at all the numbers. I'm pretty sure it's correct. This out of all the things are correct. Because this is something that is really important as a storage administrator and as a file system administrator or a Linux administrator. You need to be able to partition things appropriately. You need to be able to understand why we do certain things with storage. Storage is a very important concept that you really can't afford to miss. If you have any questions, mg@southeastern.edu, please email me. If you don't, then I will see you in the next one. Have a good day.